Okay, hello everybody and welcome to discussion 5. Today we're going to be talking about some concepts that we've seen in lecture, but I want to make sure you understand completely. So we're going to go over nonlinear elements and how we linearize them. We're going to review some basics of semiconductors, and then we'll go over some example diode circuits. Okay, so first I want to talk about nonlinear elements. And so oftentimes we take our linear elements for granted. So our resistors, our capacitors, our inductors. And that's because analyzing circuits is really, really difficult if we don't have linear elements. And so that's because when we analyze circuits, what we're really doing is solving systems of equations. Now, just only thinking of circuits as systems of equations can be dangerous because you can lose some intuition. But at its core, the operation of solving a circuit is just solving a system of equations. And so a lot of these times, the equations are relating voltages and currents, right? And so when I talk about a nonlinear element, what I'm referring to when I say nonlinear is the current to voltage relationship or characteristic, right? And so those current to voltage relationships, like impedances and things like that, are variables in our systems of equations. And if those current to voltage relationships are nonlinear, then all of a sudden now we have equations with voltages squared and things like that, where we have multiple solutions and increasing complexity. And in general, it becomes a huge headache to solve any circuit that's nonlinear. And so we like all of our circuit elements to be linear for this reason. And what that means is even if a circuit element isn't linear by nature, we often approximate that element as a linear element, or more specifically as a piecewise linear element. And that way we can then analyze the circuit as if it's filled with linear components. And so this concept of an IV characteristic is something that we will see over and over again the more we work with diodes and specifically transistors. And so what that means is just, how does the current through device relate to its voltage? And so for a resistor, we have a pretty basic relationship, right? It's a linear relationship. And so the IV characteristic looks like a straight line, where the slope of this line is actually 1 over the resistance, right? So because the resistance relates the voltage and current, we can say that that slope, the current over the voltage, will give us 1 over the resistance. So it's like a conductance. Now, let's say I have another resistor. Pretend that line was straight. I have another resistor with a steeper slope, right? Because these slopes are inversely related to the resistance values, we know that this steeper slope actually means that R2 is smaller than R1. So this is just something to be careful of when you're looking at IV characteristics. Is larger slope doesn't mean larger resistance, it means larger conductance. Let's take a look at a capacitor's current voltage characteristics. Specifically, if we fix the variable S, the Laplace variable, right? If we fix S, that means we are fixing the frequency. So we're looking at the current voltage relationship at a specific frequency for this capacitor. And so again, as long as we fix the frequency, our current voltage relationship will be linear, where the slope then is 1 over the impedance of the capacitor. We know the impedance of a capacitor is 1 over SC. So the slope is just SC. And so Obviously, the slope will change if we change our frequency, but the idea is at a given frequency, a capacitor is a linear element as well. Moving right along, we can do the same thing for an inductor, right? I'm still going to fix my frequency, right? And then I will see that I have a linear voltage current voltage relationship. And again, the slope of that relationship is going to be 1 over the impedance of my inductor. And so I guess I'll be consistent, 1 over the impedance ZL, or the impedance of an inductor, which is S times L. Okay, let's go to a diode. So the actual IV characteristic for a diode might look something like this. All right, where we have some kind of turn on voltage here, this is some reverse saturation current there. Then we have an exponential growth. Well, now we have an element that is no longer linear. But like I said, what we will do is we will take this element and create an approximate model for the element, which we call a piecewise linear model, right? You're familiar with piecewise equations, an equation that's defined differently for different subregions of the domain. And so in this case, we look at the voltage applied across the diode, and we say that below, well, I guess I've drawn my diode turn on voltage a little differently here. And so if I said my VD0 was there, my turn on voltage, then I would approximate it like this, right? Where any voltage above VD0 gives me the same, any current through that diode will give me the same voltage drop, VD0. And so, like I said, this is a piecewise linear function. So we have 2 regions, the off region, right, and the on region. And so this is where our diode constant voltage drop model comes into play. So the off region, we just model the diode as an open circuit. And then the on region, right, we model the diode as a voltage source. With drop VD0. Right, so we've taken something, an IV characteristic that is clearly nonlinear, and we've created a piecewise linear model from it, which now means that, yes, we have to do 2 different analyses, right? We have to analyze the region where the diode is off and we analyze the region where the diode is on. But each of those regions, we have a linear element. And so our job is much easier now in terms of the actual math we have to solve. Lastly, we can talk about MOSFETs, which you're just starting to see more of. And so here we're plotting the drain current of a MOSFET versus its drain to source voltage, VDS. And so we actually will get different curves depending on our gate to source voltage, VGS, right? And so depending on what our VGS is, we will see different curves. And that's indicating this direction as we go from bottom to top is an increasing VGS, right? And you'll learn more about this later, get more comfortable with these MOSFET IV characteristics later. But given a fixed VGS, so I'm going to fix VGS, then let's say I fix it in the middle, then I can actually take my nonlinear kind of clearly curved function and create a piecewise linear model again, right? Where I take the slope of the linear region and keep that constant up until the knee. And then I take the slope in the saturation region and keep that constant past the knee. And so again, we have two regions now that we've created, but in each region, this device has a linear IV characteristic. And just for reference, well, not all the way this way, but the right of the knee, so when the voltage is higher than that saturation voltage, then we're in the saturation region. And when VDS is lower than the saturation voltage, we're in the linear region. Right, so again, we have two different regions to analyze, but in each of those regions, we have a linear relationship between current and voltage. Okay, and so this concept of linearizing a nonlinear element is very important because it allows us to solve circuits of complexity that we wouldn't normally be able to solve, especially by hand. Moreover, the idea of linearizing a nonlinear element actually oftentimes refers to the same thing as a small signal analysis, where say we have our curve and we actually bias our device with some DC voltage across VDS, and then we apply an AC excitation atop that DC voltage, right? And so we're kind of taking our VDS voltage and we are picking a point, which is our bias voltage, and then wiggling that voltage about that point. And so what we see is similar to the VTC in Lab 2, where we have to stay on this curve. And so our output ID, you know, we can see in the saturation region, we have this bias value, call I bias, and then it's going to have some small amplitude of oscillation there. But the slope in this saturation region is so shallow, which means the actual effective resistance from drain to source is very large, right? So that means that I can actually move my VDS a pretty significant amount about that bias point without seeing much of a swing in my my drain current ID, right? And so small signal, this is not the best example for small signal because we're basically taking a portion of the curve that's already pretty linear. But the idea with a small signal analysis is if I have some IV characteristic, arbitrary IV characteristic that's very nonlinear, right? The idea of small signal is that I pick a bias point, and that bias point is in a very curvy part of my IV characteristic, right? And so I can move along the curve, but the problem is if I move a significant distance along the curve, so if I take that bias point and I wiggle it too much, oops, then I will really be traversing the full curve, or I should say that, you know, I'll be traversing that curvature such that my IV characteristic will just be very nonlinear, right? So this is like a large signal excitation. If I want this to be linear, what I have to do is keep my amplitude very small. And so if I keep the amplitude very small, and the amplitude of my, in my voltage here is what I'm talking about, then if I kind of zoom in on this portion of the curve, right, smaller the segment of the curve I'm looking at, more linear it looks. So I'll just say, because I'm zoomed in so far, I can't draw a straight line. This looks almost linear. And so it's kind of like the idea where you have a slope of a tangent line, right? If you just were able to take the slope at one point on your curve, that's a similar concept to biasing at that point and only applying small excursions from that bias point. And so this is like the small signal excitation now, where it looks big because I've zoomed in, but really it's so small that the portion of the curve it traverses, it looks linear. And so this is another way where even if I don't have a curve that has, is mostly linear, like these ID VDS curves, where I can see they're already almost linear. I can very easily approximate them as piecewise linear. But even if I have a curve that's very nonlinear, as long as I am cognizant about my signal amplitude and using a small signal, I can make this device act linear for me. Okay, and so this is going to be a very important concept as we move on to transistor circuit design. And so make sure that you're familiar with how important and nonlinear elements are and how important it is that we linearize them. Okay. Now moving on to talk a little bit about semiconductor types. This is going to be mostly review because of everything that you've seen in lecture, but and actually these labels are a little misplaced. So this is the undoped silicon and this is the doped silicon. And so if we look at the crystal lattice in a semiconductor, we see that we have groups of silicon atoms, each of them with 4 valence electrons, and each of those, valence electrons forming a covalent bond with an adjacent silicon atom. Now, here we are showing an electron that's actually left its covalent bond, and in its place, it's left a hole. Oops. And so a hole is, if you're struggling conceptually to understand what a hole is, I like to think of it as a bubble almost, right? Where the analogy is that a bubble is a lack of water or of a liquid, right? And so if I watch a bubble move up my glass, I can think of that as the air or the lack of liquid moving up, or I can think of it as the liquid kind of filling that bubble downwards. And so the electron in this case is the liquid and the hole is the bubble, right? Or the lack of liquid. And so in this case, right, we have, I've said this is undoped silicon, yet we still have free charge carriers. And these free charge carriers are actually what we call an electron hole pair. It's because these charge carriers in what we call an intrinsic semiconductor. So an undoped is the same as intrinsic. So when we get electrons and holes in an intrinsic semiconductor, they are always associated with a carrier of the opposite type, right? Anytime I have an electron, there's going to be an associated hole and vice versa. And that's because these electron hole pairs arise due to thermal excitation, right? There weren't extra electrons in this silicon, but the electrons that were there every once in a while will break free of their covalent bonds and create a hole in their absence. Now, that's our thermally generated electron hole pairs. So, temperature dependent concentration there. If we go over to doped silicon, right? I haven't written the type down yet, but we'll get to that. And so what's happening here is that we have what's called a donor dopant, right? Or a donor atom coming in. And donor and acceptor, those terms refer to electrons. So whether an atom donates or accepts an electron. So this donor comes in and we know it's going to donate an electron. So it makes its way into the lattice and it sticks right in between our silicon atoms. But because this donor atom needs to form the 4 covalent bonds with its surrounding silicon atoms, it actually is going to have one extra electron that doesn't fit in. So the extra electron is actually just floating around in between the atoms in the lattice, and that's now a free carrier. And so we've donated an electron to our semiconductor, and we might still have, say an electron hole pair here or there due to the fact that we are at some non-zero temperature, but the concentration of electrons due to dopants is going to be much higher than the concentration of thermally generated carriers. And so we call this type of material, so I'm going to say this is an electron hole pair, EHP. And we call this type of material N-type silicon, right? Because it has more negative charge carriers, in this case electrons is what we're referring to. And so we call electrons the majority carriers and holes the minority carriers because it's N-type silicon. And one thing to note is if this charge carrier, the electron, leaves for some reason, so it could leave due to diffusion, it could leave due to a drift, so an electric field pushing it away. But if it moves away, then that nucleus from the donor atom had a +5 charge in order to balance out those the 5 valence electrons. And while that free electron is nearby, that +5 charge, is still balanced out and we have neutral charge in our semiconductor. But if this free electron, say, moves over to a piece of p-type silicon, then we now have a charge imbalance and we actually have positive, what we call fixed charge, due to the bonded donor atom that has its +5 charge without all 5 electrons to balance it out. And that's why N-type silicon, when N-type silicon is depleted of carriers, which is what we're talking about, right? The depletion of carriers is when the electron leaves. So when N-type silicon is depleted of carriers, we get positive fixed charge. Okay, you can probably guess what type of silicon this is by process of elimination, right? P-type. And it's the same concept, just flipped. So we have some acceptor, which again accepts electrons. can't tell if I'm just gonna see all of these drawings that I've been drawing and then have been disappearing, or if they're gone for good, but we'll see. Anyways, so we have an acceptor which has 3 valence electrons. When that acceptor shows up in our semiconductor, it goes into the lattice and forms those 4 covalent bonds. However, it only had 3 electrons to begin with. So it will actually pull an electron away from another covalent bond and leave in its place a hole. And that hole is a mobile charge because it could move to another bond, right? If another bond filled that hole with its electron. So I could say this electron then might move there and create a hole in its place. It's like every time I switch my pen, it erases the last couple of lines. Okay, but I think you get the point. So we, in this case of a p-type semiconductor, if that free charge is depleted from this region, we will have a +3 kind of charge from our donor, sorry, excuse me, our acceptor, but we don't have that hole around any longer to balance out the +3. So we actually have less positive charge. And so our, I should say, we don't have that hole to balance out all the 4 electrons kind of around the fixed acceptor. And so if that hole leaves, we will be left with fixed negative charge. And so that is why p-type silicon, when we deplete it of carriers, is full of fixed negative charges. Okay, so that's just kind of a brief overview of the semiconductor types. Let's move along, talk about p-n junctions a little bit. So p-n junction is when we connect a piece of p-type silicon to a piece of n-type silicon. Typically, we can look at a p-n junction as a diode actually, because they're the same thing. Diode is a p-n junction. And so if this is a diode, the way we would typically hook it up or bias it or get current out of it, I should say, is by connecting a forward bias, which means the positive potential is connected to the p-type, negative potential is connected to the n-type or the cathode, right? And in this case, we get our diode voltage drop here, VD, and we get some diode forward current, IF. Now, on the right, we have an image of kind of what's happening in this diode, where, like we just talked about, we get depletion regions full of fixed charge, and the p-type depletion region has a negative fixed charge, and the n-type depletion region has a positive fixed charge. Now, we also have 2 current components labeled here. So ID is the diffusion current. So we see ID because holes, right, are in abundance on the P side, and there are very few holes at all on the N side. So those holes want to diffuse from P to N, and that's the diffusion current. Similarly, we have electrons diffusing from N to P, but because it's a negative charge carrier, movement from right to left indicates a current from left to right. And so both of those diffusion components will add together to get the total diffusion current. And we also have IS, which is the saturation current or reverse saturation current, and that's due to drift largely. And so that occurs when we have a reverse bias such that we create such a big depletion region that we no longer have really any diffusion at all. And in that case, we will have a depletion region with this fixed charge that actually creates an electric field, right? And the electric field, just remember, is the direction that a positive charge will move. And so if that electric field is from right to left, we will see positive charge moving from right to left, which is the same direction as IS. Okay, so this barrier voltage, that's kind of like the voltage that that you need to overcome in order to close that depletion region and get the diffusion current. And so a diode turning on is actually just you kind of bringing the depletion region edges together and making the depletion small enough such that diffusion current can take over. And so the actual significant current you see in a diode isn't due to electric fields, it's due to diffusion or concentration gradients. And that's important to know and understand. So just moving along, looking at how PN junctions react to different applied voltages, right? So if we have a PN junction that's open circuited, we know we'll have no net current flowing out of the terminals, right? There's nowhere for current to flow, but we actually do have internal current that's equal and opposite. And we have that because we have those thermally generated carriers. So we will have, every once in a while, we'll have a hole, maybe we'll diffuse from the P side down to the N side, and vice versa, we'll have electrons diffusing from N side up to the P side. And then we will get minority carriers, so electrons on the P side will hit the edge of the depletion region and be swept across due to the E field, right? So similarly, we'll have holes on the N side, which are minority carriers. If they make it into the depletion region, they will be immediately swept from the N to the P side due to the electric field. And at equilibrium, what we have is that these two current components cancel each other out and are equal and opposite. So we have as many charge carriers moving from P to N as we do from N to P. Now, the difference in the depletion region's widths on either side of the junction has to do with carrier concentration. And that's because when we create this depletion region, the fixed charge on the P side has to be equal and opposite to the fixed charge on the N side. And so if the carrier concentration is different, then the volume needed to meet that, to get the same fixed charge, is going to be different on the two sides, right? Because the concentration tells you how many charge carriers you have per unit volume. And so if you're given a picture like the one left with a smaller depletion region on the P side than the N side, that tells you that you have a higher concentration of carriers in your P side. So you have Na, the acceptor dopant concentration, larger than Nd, the donor dopant concentration. You can see that just based on the fact that you have 6 charge carriers kind of in a smaller space on the P side than on the N side, right? Because they're more spaced out on the N side. If we go over here, this is a plot of the charge distribution, which helps you visualize the concept that these two charges need to be equal and opposite. And so in this case, the area under the curves need to be equal and opposite. And you can see that we have kind of two charges, Q minus and Q plus, and the absolute values of those are equal to something like A times XP, which is a volume, times Na, which is 1 over volume, that's atoms per volume, times Q, which just tells you how much charge you have per atom. So that gives you how much charge you have in a given volume. And so what you need to do is, when you're solving problems like this, is you should set Q minus equal to Q plus, because like I said, the two charges have to be equal and opposite. And if we do that, we get AQ and AXP is equal to AQ and DXN. The cross-sectional area, the charge cancel out, and we get that XP over XN equal to ND over NA. Right. So this doesn't depend on anything except for the initial carrier or dopant concentrations, right? And so the ratio of the two dopant concentrations will tell me the ratio of the two depletion widths in the two regions, and that'll stay fixed for a given doped material. Okay. Lastly, we have the built-in voltage, that voltage barrier, right, which is basically at a height V0 whenever we open circuit our PN junction. Moving on to other cases where we apply voltages. So again, open circuit, we have ID is equal to IS. So we have some total current, which is equal to 0. And then we have ID is equal to IS, equal and opposite, right? Remember, we have our fixed charge here. We typically draw a fixed charge with circles around it. Well, I guess I was drawing our mobile charge with circles around it earlier too. So watch out for that. If I do that, let me know. And so for the open circuit, we have this, built-in voltage still. And then if we apply a reverse bias, what we do is we actually increase that built-in voltage, or the effective barrier voltage. So when we apply a reverse bias, what we do is we increase the depletion region such that we have less atoms that are able to diffuse across. And so our ID, the diffusion current, is going to go down to the point where IS will dominate. So IS again is the diffusion, sorry, is the drift of minority carriers across the depletion region. So say that again, IS is the drift of minority carriers. So here, this is a, I'll stop drawing circles. So this is a hole, right? So that's a minority carrier in the N-type silicon. And we have this E field, which is the direction a hole will move. And so if that hole makes it to the edge of the depletion region, it will get swept all the way over to the P side. Similarly, an electron minority carrier in the P side will get swept all the way across to the N side if it hits the depletion region. Okay, and so basically most of our current is just coming from this drift of minority carriers, and the minority carriers, those are thermally generated, right? We can't have a dopant introducing both minority and majority carriers, and so minority carriers are just thermally activated, and that tells us that the saturation current is actually highly dependent on temperature, not on doping. Okay, and so you can see now our potential barrier height here is larger than just VO, right? We've increased the barrier height, and that's another way of thinking about this, right? The barrier is keeping us from diffusing, and so we have less diffusion because we've increased the barrier height. Lastly, the most kind of important, I think, biasing scheme is the forward bias, where we apply that positive voltage to the P side, negative voltage to the N side, and we get current here, forward current. And you can see we've reduced our potential barrier to the point where that diffusion current just is able to completely dominate the saturation current. And so that VF is equal to VD0, the turn on voltage of the diode, right? And just for reference, the diode characteristic looks something like this, where we have below VD0, we have our negative IS, reverse saturation current. And then above VD0, we have that exponential growth of our current, okay? And you'll see in the next homework coming up where that current comes from physically, okay? So that's p-n junctions with applied voltages. Let's take a look at some diodes, just quickly go over the models we have. And so for an ideal diode, again, we have to take into account the two different regions. And so we have the off region, and switch colors. We have the off region where we treat that as an open circuit. Then we have the on region where we treat the diode as a short circuit. And so this is the simplest model you can have for a diode. It doesn't assume any voltage drop, and it doesn't assume any series resistance. And you can see kind of how the reverse bias corresponds to off here. The forward bias corresponds to on. So what we've done is we've taken the actual diode IV characteristic and just made the most simple piecewise linear function out of it. And in reality, the diode is not going to behave quite like this. And so we can use what's called a constant voltage drop model, which takes the same exact shape, but just shifts the curve such that it better represents the diode's turn-on voltage. And to do that, all we need to do is create some voltage drop independent of current. And that, by definition, is a voltage source. And so when we use the constant voltage drop model, we still have our off state is an open circuit. All diodes are basically, you can approximate them as an open circuit when they're reverse biased because that reverse saturation current is so small. I shouldn't say all diodes. Zener diodes actually have a low reverse breakdown voltage, so you can operate them in reverse bias mode. And all diodes will actually break down at a certain point. And so you'll have, way back here, you'll have some avalanche breakdown where the voltage gets low enough that it gets negative enough so that the current flows in the opposite direction. But for now, don't worry about that. This is the constant voltage drop model. With all of these models, it's important to understand that we are taking something that's new and nonlinear, and we are turning it into a linear device with models that we know, things like a short circuit or a voltage source. And there's nothing special about these models. So once you replace the diode with its model, don't worry about, is it a diode or things like that. Just analyze the circuit, trusting your instincts and trusting what you know about the model. Okay. So oftentimes students will get confused thinking there might be some exception to the rules they've learned. But no, that's the whole point of the model, is that we can stick to the things we know, even when we're solving new circuits. Okay. Speaking of new circuits, here's the most common kind of diode circuit you'll see probably is a rectifier. So the idea behind a rectifier is that we want to take an AC signal or an AC voltage and turn it into a DC voltage. And so again, we have to kind of break this up into two regions of operation. And chances are good that those regions will coincide with the different signs of our input. And so we can take our AC input and we can look at first, when it's greater than 0, and it's less than 0. And so oftentimes these diode circuits is the way to do it. And essentially what we can do, because this is such a simple circuit, is we can see if Vn is positive, we are going to create a voltage drop across the diode Vd and a voltage drop across the resistor Vo. Our current will flow through both of them, and we will basically get the same output, excuse me, as the input. The output will track the input because our voltage source is ideal, has no series resistance or source resistance. However, when the input goes negative, now all of a sudden, in order for current to flow the opposite direction, we would have to reverse bias the diode, in which case we know that we have to treat it as an open circuit. So we are using the ideal diode model now. We're not using the constant voltage drop model. And so on those cycles, where the Vn is negative, right, this resistor is just connected to ground with no current flowing through it. And so this Vo is also essentially ground. And so our Vo is going to be 0 when Vi is negative. So this might not look quite like a DC signal, like I said we're trying to make, but imagine I put a capacitor here and shunt with my output. Now, every time I hit my peak, it'll take some time to discharge. So I'll get back to the next peak and it'll take some time. And so I can see, if I were to draw this signal like this, it's not quite a flat line, which is what a DC signal would be, but it's almost like a DC signal with some variation, which we call ripple. And there are multiple versions of rectifiers, many, I should say most better than this, but it's a good starting point for understanding how diodes can work in circuits. Okay, so another example of a diode circuit is doing DC analysis. So anytime we want to analyze diodes in circuits, especially when there are multiple diodes, we need to make an assumption about the diode's state. And so oftentimes, if you have no idea where to start, just assume the diodes are all on. And what we will do is we will analyze this circuit, and the things we need to check for are the diode voltages and the diode currents. And so if the diode voltages or the diode currents, if anything, contradicts the assumption we made about the diode being on, that means our assumption was wrong. Okay, we'll see what that means in a second here. So if the diodes are both on, I'm going to take the ideal model, short circuit them, and now my VB is connected to ground directly, right? 0. I should say this is VB here, voltage at node B. Similarly, my V node here, that's directly connected to VB. So now I can analyze the current through D2. ID2 is going to be equal to Ohm's law, 10 volts minus 0 volts over 5 kilo ohms is 2 milliamps. So if 2 milliamps of current flowing through that 5 kilo ohm resistor in order to get 10 volts of drop, that 2 milliamps will flow down through D2, right? I'm fine with that. D2 is going to have 0 volts across it, which is fine for the ideal model. And then I can look at D1, right? To do that, I'm going to actually take a look at the current flowing through this resistor, which I'll just call IR. That current flowing through that resistor I can find based on the VB that I assumed. And so I'll say that I can actually move my writing down here. And so IR then becomes VB minus the other side, right? It's -10 over 10 kilo ohms. Remember, VB is 0. And so I just get 10 over 10K. So I get 1 milliamp. Okay, so if I do KCL at B now, hopefully you're starting to see what's going to happen. But I get that ID2 combines with I, right, the I defined here, to get IR. Well, the voltages that I've assumed create currents that don't quite make sense, because now I have ID2 is 2 milliamps minus, I should say, plus I is equal to 1 milliamp, which means that I has to be -1 milliamp. Well, if I is -1 milliamp, that means it's actually flowing in the opposite direction, right? It's flowing upwards. But like I said, that is a contradiction to the assumption that D1 is on, because if D1 is on, it needs to have a current flowing from P to N. And so this is the kind of contradiction that you can see and say, okay, this means that I made the wrong assumption. And now it's not always the case, but oftentimes I can learn from that assumption and say, okay, well, D1 gave me contradictory answer. So I'm going to assume it's actually off, that I was wrong about D1. And I'm going to assume that I was right about D2 and leave that on. Well, if I short D2 and open D1, I actually just get a circuit that looks like this, where I have 10 volts. I have my 5K. I have my VO, V, which is actually referenced to ground. So that's something to be careful with when you have these rails. D1 is open, so that ground is not doing anything. And then D2 is shorted to the 10K resistor, which is connected to my negative supply. And so I have something that kind of looks like a voltage divider. And so in order to figure this out, what I can do is I can take the total current, ID2, through this voltage divider is going to be equal to, again, Ohm's law, where I take the total series resistance and the total voltage, and take the ratio of the two. The total voltage drop is 20 volts, and that's dropping over 10K plus 5K. So I have 220 over 15. So I have 4/3. So I have 1.33. There's a K in the numerator or denominator, so that's milliamps. Okay, so this is the total current. And now I can figure out what V should be based off of that current. Okay, so V is going to be 10 volts minus, actually I like it better this way, -10 volts plus 10K times 1.33 milli. I like that because I can just take 10K, easily multiply that to get 13.33 volts. And so that gives me V, right, 3.33 volts. I can see that that voltage is below 10 volts, right? So that makes sense that ID2 would flow downwards. And there's no contradiction. And so that means this assumption is right. And this is the final voltage for V and for ID2. Okay. So this is generally how you solve these diode circuits. As you get more comfortable, you'll be able to make educated guesses about which diodes are on and which are off. But the nice thing about these methods are that as long as you follow them, you'll always get to the same answer, right? It doesn't matter where you start, what assumption you start at, as long as you're doing this correctly, you'll get to the same answer. And so the last thing I want to talk about is this diode circuit using op-amp. And so similar to before, I want to split this up into two regions. So we're given an input triangle wave, amplitude of 1 volt, and we're given this circuit. I'm told to assume the diodes are ideal and sketch the output waveform. And so I'm going to split my input waveform into the two cycles that I know I'm concerned with, which is when Vs is greater than 0 and when Vs is less than 0. So these are the two cycles. So first, when Vs is greater than 0. So now I'm seeing the case where I actually need to kind of think about each cycle, and each cycle I need to think about which diodes are on and which are off. So kind of two problems, whereas the DC circuit we solved was just kind of one problem. And so I can actually figure out or rule out one case without writing any equations down. And that's the case that both diodes are on. So if both diodes were on, I would be shorting my output to my input, and I would be shorting VO to my op-amp output. Now, if I have this feedback network, that means that I will have a virtual ground here at my inverting terminal. If I have a virtual ground there, that means I have a virtual ground here, right? And so if I look at the currents, right, if Vs is greater than 0, then I will have some current flowing in, IN. The current here is 0, right? No current flowing to my op-amp. I can see that VO is grounded, virtual ground, because the other side of D1 is virtual ground and D1 is a short in this assumption. If VO is ground, that means the load current here is 0, right? No voltage across the resistor. It also means that the current here is 0 because there's no voltage across the 10K resistor. Now, all of a sudden, I see that the only place for IN to go is through D2, but that would be flowing backwards. Not only that, but the D1, right, doesn't have any current flowing through it in this assumption, because all of IN would have to flow back into the op-amp's output. There's nowhere for it to go in the other direction. And so I'm going to erase this, but just take a look at it and realize that this is, I'm just following the ideal op-amp laws and Ohm's law and KCL. And from this, I can determine that I know both diodes won't be on at the same time. And so instead, I'm going to make an assumption that D1 is off, excuse me, is on, and D2 is off. So if D1 is on, but D2 is off, I get something that looks just like an inverting amplifier. I'm going to draw VS with this polarity because it's a positive cycle. We're still looking at case 1, or region 1. I have my op-amp, non-inverting terminal grounded. D2 is open, so I don't have any direct connection from output to input anymore. Then D1 is shorted, so VO and the op-amp output become the same. I just get something like this. Now, if I think about the current flow, right, VS will cause IN to flow this way. We know that IN has to flow through the feedback network because no current can flow into my op-amp inverting terminal. And then that IN will split between RL here and the op-amp output. And that component of IN going this way, call that ID1, right? It's a current flowing through D1 and it's flowing in the direction we expect. And so this assumption is right. I'll just say this is generally like R2 and R1, right, for my inverting amp. And so this assumption we made brought up no contradictions. And so in this case, our gain, we know is just negative R2 over R1. Well, we have 10K, 2K, so we have a gain of 5, negative 5 volts per volt. So for regions 1, where VS is positive, we will just get an inverted signal with 5 times the amplitude. Okay, so that's the case 1. I'm going to try and fit case 2 on the same slide. And so case 2, well, I'm just going to assume the opposite. So I'm going to assume for case 2 that D2 is on and D1 is not on. And so what happens in this case is I am actually connecting my output directly to my input. And so in this case, I have something that looks like this, where my input is now negative. Still connected to my inverting input, my non-inverting terminal grounded. I have my kind of my wire just connecting output to input. Then I'll draw the other stuff just so we can see it. That's my VO. That's important because that's the voltage I'm plotting, right? That's my RL, my R2, and I forgot R1 here. Okay, so I still have negative feedback, right? So this is still virtual ground. So if that's ground and VS is negative, I will actually have my input current flowing out of my into my source and kind of out of my circuit. So IN is going to flow that way. Now, IN could come from both the R2 branch and from the op-amp output, except I've said this inverting terminal is virtual ground. And so if that's ground and the other side of RL here is ground, I basically have something like this, right? It's not exactly like this because it's a virtual ground. But if I have two resistors and no voltage source, right? What's the voltage in the middle going to be? It's just zero, right? There's no place for voltage to be generated. And so it also means that the current here is zero, and that means all of IN is coming from the op-amp output. So let's think about the diode current. Well, IN in this case is just equal to ID2, right? The current flowing through D2. And so the current direction is what we expect, no contradictions. This was the right assumption. And VO for negative VS is just zero. Okay, so region 2 of the cycle. VO is zero. So my signal will look something like this, where it's like kind of like a rectifier, half-wave rectifier, inverted with gain. Okay, that's all I have to talk about. So please feel free to ask questions in office hours or Piazza if anything didn't make sense. But thank you, and